Monday, it's like, I'll take a lap, we don't have.
Yeah, we don't class Friday.
Yep. So, how y'all feeling?
Alright.
Fair enough. Break is nigh. Hopefully that'll be a good time for everybody. Does anyone have any questions before we get started today? Tail end of 13, and today we're going to do the bits of 14 that I wanted to cover. I've got a couple of problems labeled 14 posted for homework. But yeah, currently 13, which has been about a week. 14 we will do in half of today. So the chapters are not always the same length. Before that, though, I want to very quickly look at the calendar. I'm sure everyone's up to speed on what's happening in the next week to several weeks. Today is March 27th, Wednesday. This Friday is Good Friday, and therefore Easter break, so no class that day. There is lab 2 day. I want to make that clear. We had normal lab this week. That does include today if you attend the Wednesday labs. But Easter break starts this Friday. That also includes Monday, April 1st, which is not a joke. And since there is no class that day, there is no lab that day. And that means that there is no lab at all the first week of April. So yes, lab today, no lab next week. And we will have class next week on Wednesday and Friday. Now to look kind of briefly at the following weeks. Week after that, the 8th through the 12th, I originally posted on my syllabus that test 2 would be April 8th through 10th. I've mentioned this before, but now I'm officially saying I am changing that plan. Test 2 will not be 8th through 10th. It will instead be 15th through 17th. Instead, the 8th will be Eclipse Day, because that is the day of the eclipse, and I plan to talk about on that day in class all of the math for gravity and orbit that goes into an eclipse, which I think is a fun way to spend the day anyway. That week, 8th through 12th, we won't have an in-person lab that week because normal lab period would overlap with the eclipse, and I don't want anyone to miss it if they're able to and want to see it. So we will not have an in-person lab the 8th through the 12th. Instead, I will give a very short out-of-class assignment that you guys can work on your own, either on your own or together over the course of that week, just so that no one has to be here in the lab room in the afternoons when the eclipse is happening. So, yes, lab this week, no lab at all next week. The week after that, we will have a remote lab, and the week after that will be test 2, which also means no lab that week. So, to highlight that. Test 2 will take place this week, technically the 15th through the 17th. And, leading into those days, I will take class time to explain exactly what will be on the test, go over more practice problems that I write and post. So we've got time to prepare for it. Just want to make sure everyone knows when it's going to be. And then we have a week after that for one more normal lab and a tiny bit more learning before we swing into exam review. Question?
When is the final day of any new content that's going to be on that test?
On this test?
Yeah.
For new content, so I'm aiming to talk about waves about this week. And so I would expect the last day of new material for this test to be the 10th, maybe just a tiny bit on the 12th. So waves would be the last thing I would discuss before the test. After the test, we've got maybe a week where I wanted to cover some bits about electricity. But that would put electricity after test 2. Electricity would not be on test 2.
Okay.
Does that answer the question? Okay. Anything else on your minds right now?
Will the test be like similar to the last one, like similar format and everything?
Yes, basically the same format. Maybe some more concept questions versus math. The first test might have been pretty math heavy. I'm not the greatest judge of that because I do math in everything, so I have to examine it a bit more closely. But the later half of the course has probably been more about abstractness than numbers. So the second test will be formatted the same way, but it might be weighted a little more towards concept questions than the first one was. Does that answer that question? Okay. But formatting will be the same, and it'll still be 105 points out of 100. That's something I do on everything. Anything else on your minds right now? All right. In that case, for learning today, my plan is to completely conclude all of the pressure-related stuff we've been going over for the past week or so. That means that we're going to, again, wrap up what the book calls Chapter 13 and very quickly skim through some pieces of what the book calls Chapter 14 that I want to talk about. But after today, we'll be done with pressure and such until we review for the test. So when we meet back up next week, it'll be something new. No. Because next week it's waves. Sound is a pressure wave. So I guess we're not done with pressure. But anyway, today we're going to conclude what we've been doing before the break. Let's say it like that. Last thing we talked about was buoyancy. This formula is called Archimedes' principle. You use it to calculate buoyant force being the force that a fluid exerts upwards on something when you are submerged in it, and this is what causes floating. Buoyant force is equal to the density of the fluid you're trying to float in, because the fluid is what determines the amount of buoyant force, not the density of the object. Fluid density times the volume of the object, namely the portion of it that is under the fluid's surface, and then times G, just the strength of gravity on this planet. Technically, it's easy. Well, you generate more buoyant force if you're on a planet that has higher gravity, but you also weigh more on a planet that has higher gravity. So whether or not you float in water on Jupiter is kind of a wash. Anyway, we talked about how we use this to calculate buoyancy and how buoyancy causes things to float. I want to briefly mention just a few last details about that one before moving on. There we go. All fluids generate buoyant force, and that does not only include liquids, that includes gases. Gases can generate buoyant force, and since air is a gas, air generates buoyant force, which means at this very moment, there is a buoyant force from the atmosphere acting upon your body. Let's calculate something along those lines. Let's take a helium balloon filled to a volume of 0.5 meter cubed, which my markers are so inconsistent today. There. So, helium balloon. Current volume is 0.5 meter cubed, which is still a lot. This might not be totally to scale, but if you made this three-dimensional, it takes up a pretty good amount of space. And next to that balloon, we have a second round object. I call it a basketball, but this is pretty big for a basketball. The point, though, is it's the same size, but it's filled with air instead of helium. So I want to make that clear. Some sports ball that is filled with air, whereas the balloon is filled with helium. Is that difference clear? All right. So they're the same size though. They occupy the same volume, the same 0.5 meters cubed. And since they are on planet Earth, they are currently immersed in air. They are submerged within our fluid atmosphere. And that means that the air is going to exert a buoyant force on these two items. The density of air on planet Earth is typically considered at standard variables to be 1.21 kilograms per meter cubed. So if you had a 1 meter cubed box of air, it would have a mass of 1.21 kilograms, which feels like a bit too big, but turns out air is kind of heavy. Given all the information that we have so far, what is the buoyant force from the air on the balloon? Force formula says we need the density of the fluid creating the buoyant force, the fluid you are submerged in. So even though the balloon is, bless you, sorry? I have 16.5? Almost. That's about 10 times too big. At least it was the last time I calculated it. We need like 6.05, yes. That's what I'm expecting anyway. We need the density of the fluid you're trying to float in. So we don't actually care about the density of helium right now. We need the density of the air that is surrounding the helium balloon. So that is the 1.21. The volume of the balloon. The whole balloon is surrounded by atmosphere, so we do want the balloon's entire volume. That's 0.5. And lastly, we need 10 for the strength of gravity on this planet. 1.21 times 0.5 is about 0.6. 0.6 times 10 should be 6, is what I'm expecting. .05. I'm remembering right from the last time I did this one. What is the unit on such an answer? Newtons, very good, because it's a force. In what direction does that force point? Up. Buoyant force always points up because it's opposing gravity. So that balloon has about 6 newtons of upward force acting on it, which is about 1.5 pounds upwards. And that is why helium balloons float. Literally, the atmosphere is pushing them upwards. Just like water pushes up on wood and styrofoam. Well, technically on everything. Now, sequel question. We have a basketball or some other ball filled with air instead of helium that is the same size. What is the buoyant force on that? Same, because this formula cares about the atmosphere's density and the volume and the gravity. None of those variables change if we look at a ball that is the same size as the balloon. So the ball has the same upward buoyant force acting on it, but it doesn't float away. Why?
Because it's filled with air.
It's filled with air, and air is heavier than helium. They both have this same upward force on them, but the ball is just heavier. Specifically, helium is about 100 times less dense than air. Last time I looked it up, it was like 0.01 kilograms per meter cubed for helium. Actually, I think I've got that tab loaded. I'll double check. That's not the right tab. Okay, it's actually 0.17. So it's actually only like 9 times less dense than air, but it's still much less dense than air. And that means that a balloon filled with air will be about 9 times heavier than one filled with helium. So both objects have the same upward buoyant force on them, but only the balloon filled with helium is light enough that this force is greater than its weight and therefore it rises. Everything that displaces air, and that includes us, generates buoyant force. So even we have a force about this size acting on our bodies. But we just weigh many times more than this, so you don't really notice it. But the lighter something gets, the more you notice it, and that's why beach balls tend to drift back down pretty slowly. They might be filled with air, but they take up enough space that the buoyant force on them is closer to their weight, and therefore it matters a bit more. But you guys have buoyant force from the atmosphere acting on you right now. Technically, you'd feel heavier if the air wasn't there. You'd also explode if the air wasn't there, but that's a separate issue. Questions? All right. Now, there's a couple more fluid pressure related concepts I want to address today. We're going to try to wrap up all of them today and then have our nice break. First thing I want to discuss is a phenomenon known as Pascal's principle and how this affects our lives. If you exert pressure on a fluid, the whole fluid becomes pressurized. If you exert pressure on one part of a fluid, the whole fluid is now under that pressure all at the same time, even if you are only acting on part of it. If I take this basketball and I exert pressure on part of its surface, the pressure that I'm adding is added to the entire gas contained within the basketball. And so the entire gas within the ball feels the pressure that I'm adding, and that's going to increase the entire pressure within the entire ball. If this was instead a balloon, something that can flex a little bit better, and I push on the balloon, the rest of it is going to start growing because the pressure I'm adding to one part of it carries through to all of it. If you squeeze that balloon, it kind of bulges out between your fingers because the part, it's not just the part that you're directly acting on that the pressure translates to. It translates to all of it. Pressure acting on one part of the fluid is carried through to the other parts of that same fluid. And over the years, humans have figured out ways to take advantage of that fact. Now, the formula that's currently on screen is just meant to show that the pressure acting on one part of a system, a fluid system, will be the same as the pressure acting on a second part of that fluid system. Because F over A is pressure. Force over area is the definition of pressure. But just because the pressure is the same from one side of a fluid to the other, doesn't mean that the forces are the same from one side of a fluid to the other. Because you can build a system where the surface areas on one side of a fluid are different to the other, and the same pressure within that fluid will generate a different amount of force on a different surface area. Now, this might be a little hard to visualize because while this does affect your daily life on this planet, it's something that does kind of happen in the background. To try to illustrate this phenomenon, the picture that's currently on screen is of a liquid reservoir. Let's just call it water for simplicity's sake. This is a big tank filled with water, and it's got two exit pipes. Like there's this whole tank that's underground, and there's only two ways that water can flow in or out of it. There's this pipe here, which is very narrow, and then there's this pipe here, which is a lot wider. Therefore, this section has a much smaller cross-sectional surface area than this part does. So we've got one fluid, like one body of water down here, and we've put it in a system where we can exert force on one side of it. This right here is a piston that's being weighed down, and the force acting on the area of water here is going to push down and cause the water to flow out of the way. This is because liquids don't compress. I mentioned when we were talking about the states of matter that liquids have no definite shape. They flow and they take the shape of their container, but they do have definite volume, meaning that this water has to take up the same constant amount of space. It can't get any smaller. So if you push down on the water over here and push it out of the way, that water has to flow and go somewhere and take up space elsewhere instead of where it originally was. And if it's no longer taking up space here, it's going to take up space over here. And if all the water is flowing from one pipe into the other, that is going to force the other plate over here, which has a much bigger surface area, to start rising. Because by pushing water out of this side, the water's now over here, it needs somewhere to go, it's going to push up on this other plate to push it upwards and take the space that it was just in. Bless you. Because all this water has to exist somewhere. It can't get any smaller, it has to take up space somewhere else. And what this principle tells us is that the pressure throughout this entire system will remain constant. The pressure we exert on the liquid over here will be the same as the pressure the liquid exerts upward on the other side. And since the two sides have vastly different surface areas, there's different forces involved on both sides. Basically, it takes us a very small amount of force to push down on the small surface area over here and push the water out of the way. And that generates a certain amount of pressure, force over area. And that same pressure will exert more force on a greater surface area plate on top of the other side. This is a machine that will multiply your force input. You can input a tiny amount of force over here, and it gets a lot bigger. You get more force out the other end. This is a hydraulic system. This is how hydraulics work, if you've ever heard or dealt with those at all. Now, maybe you don't care about hydraulics, which is fine, but a lot of machines do make use of them. Historically, one example of that is the machine that lifts your car up at the car shop. They aren't all hydraulic. In fact, some of them are probably either totally mechanical or could be pneumatic. But some of them were built using hydraulics, meaning that there's a liquid reservoir under the car shop. One side of that reservoir is pressurized, and that pushes the liquid up underneath your car, acting upwards on the machine that your car is currently parked on top of, literally forcing the whole thing upwards so that mechanics can work on the underside of the vehicle. And again, the purpose of this machine is to basically multiply the force input on one side to get a bigger force output on the other. The pressure from one side to the other is constant, which we'll prove in a second. But the force on the different surface area plates is different even because of the same pressure. If you can build a machine like this, we're about to demonstrate that you can use it to theoretically lift an entire car with one arm. To demonstrate that math, F1 over A1 equals F2 over A2. Again, this tells us that pressure 1 equals pressure 2. The pressure is constant throughout the entire system, because that's what F over A is. But that same pressure will create different forces on the different cross-sectional areas of this liquid system. On the car side of this liquid system, the cross-sectional area of this output pipe is 4 meters squared, which is a lot. This is again 1 meter squared, so 4 of these stapled together, which if you reshape it a little bit, that's about the size of some vehicles. So the area on the car side is 4 meters squared. And the force output required on the car side, you have to exert a certain amount of force to lift the vehicle. This SUV has a mass of 640 kilograms. In order to lift it, you have to exert enough force on that mass equal or greater than its weight. So for the force 2, I'm going to put something equal to the weight of the car. Its mass in kilograms times 10, it's just mg. Same as we've been using. Fg equals mass times 10. So mass in kilograms times 10. This is the needed amount of vertical force minimum to lift the car. And this tells us that in order to get the car elevated, you need a certain amount of pressure. It would be 6,400 divided by 4, and that would tell you the amount of pascals needed to pressurize this system. Now, on the other side, we're going to use the narrower cylinder to create that amount of pressure. So all the way somewhere else within this garage is a different cylinder. It's a lot narrower. I specifically wrote the example so that that area, that 0.04 meters squared, is probably about the size of a button that you could push. And we are going to calculate how much force you would have to exert on it to lift a car by yourself with the aid of this machine. So again, you're going to push down on this side, generating a certain amount of pressure. That pressure remains constant through the system, but it's going to exert more force on the greater surface area plate on the other side. So again, the purpose of this device is to multiply your force input. Any questions on how I set this up before I get to the final number? All right. Gotta multiply both sides by 0.04, so F1 equals 640 times 10 over 4 times 0.04, which, if my memory serves, please correct me if I'm wrong, it's about 64 newtons. You could use 64 newtons of force to lift this car. That's about 15 pounds. Theoretically, you could lift the car with one arm, with the aid of this very big hydraulic system. So that is what hydraulic systems are, and that's why they were invented. They allow us to multiply force input to be able to get more force output with the help of a liquid reservoir by keeping pressure constant. Now, even if you, first of all, questions? Okay. Now, even if you don't care about cars or hydraulic systems, there's one hydraulic system that you undoubtedly use on a daily basis as long as you drive a car, and that is your brakes. You've heard of brake fluid, correct? If you know about cars, you know this is all review. But if you're less familiar with cars, when you push down on the brake pedal, you are physically pushing onto a liquid-filled piston filled with brake fluid. And that cylinder, this is not exactly how it's drawn, but just to demonstrate, that reservoir expands to a much bigger surface area, and then an output plate pushes a greater amount of force into your wheel well using your brake pad to exert force on the tire to slow it down. So a hydraulic system pushes on brake fluid. You exert about 10 newtons here, you maybe get several hundred newtons of output on the other side, which is enough to slow down your car. And that's why your car needs brake fluid. Sound good? All right. That is officially the end of what the book would call chapter 13. I want to very briefly mention a few things from what the book calls chapter 14. Again, the course is based on the textbook, but I'm kind of cherry picking the parts out of it that I think are important. So there's just a couple last details about pressure that I want to point out before we break for the weekend. Firstly, I want to point out this system works best the way that it's been described because you're using a liquid and because liquids can't be compressed. I said again, liquids have definite volume, which is why if you push on part of the liquid, it flows out of the way and takes up the same amount of space on the other side. That is different to gases. Gases don't have definite shape nor definite volume, meaning that you can take a gas and pressurize it to make it smaller. When you push on this liquid, it doesn't shrink, it just flows. If you press on a gas, you can actually make it shrink. Meaning if you, instead of water or brake fluid or whatever system fluid they use in modern hydraulics, if you filled this with just air, the car probably wouldn't rise at all, if very much. Instead, what would likely happen is you'd just be pressurizing the gas inside of the system, making the gas take up less and less space until the pressure rose to a point where maybe the car would budge. Gases do compress, and we refer to this phenomenon as gas law. This is at least part of gas law. Might sound familiar if you've taken some chemistry courses. What gas law says is when you pressurize a gas, it will change its volume proportionally based on the pressure. There's a formula for it that says pressure 1 times volume 1 equals pressure 2 times volume 2. Say on this side, we've got 1 unit of pressure and 1 unit of volume for simplicity's sake, like in this basketball. Let's say that our pressure unit is just 1 atmosphere of air pressure, and our volume unit is basketballs. So 1 atmosphere times 1 basketball, we've got 1 on this side of the equation. That product remains the same on the other side, but if I, instead of 1 atmosphere of pressure, start squeezing the basketball in order to exert 2 atmospheres of pressure on it, if I double the amount of pressure that the ball is under, this formula says that the ball will shrink down to half the volume. On the left side, 1 times 1 is 1. On the right side, double the pressure requires half the volume to be equal to the first side. On the left, you'd have 1 times 1 is 1. On the right, you'd have 2 times 0.5 is 1. If you double the pressure on something, it shrinks. If you double the pressure on a gas, it shrinks to half its original size as long as you keep temperature constant. This is in part why a beach ball left out overnight will deflate. The gas inside the beach ball will respond to the changing atmospheric pressure as the night goes on. So you can compress a gas. You can make the gas smaller. And that is why you don't use gases within a hydraulic system. You have to use liquids. There are some systems that do use gases to accomplish the same thing as a hydraulic, but they have to be built slightly differently to accommodate the change in volume. They have to start manipulating temperature, and we call those pneumatics instead of hydraulics. So hydraulic uses liquid, pneumatic uses gas. All right so far? All right. I want to apply this to a couple examples that you might deal with on a regular basis, semi-regular basis. To kind of write out the numbers to something similar to what I just said a second ago. Let's say at normal atmospheric pressure, we have a 1 cubic meter balloon. Which is big, by the way. So on our initial side, we've got a pressure of 1 atmosphere's worth of pressure. Instead of putting in the entire Pascal number, I'm just going to use units of atmospheres for simplicity's sake. So 1 atmosphere's worth of pressure times 1 meter cubed of volume. And that's the balloon normally before we let it go. If you release it, it's going to float away. And at a certain altitude, the pressure is going to start dropping. There's a certain point where the pressure will, say, be cut in half. So you'll reach a certain height where the air pressure will drop to half an atmosphere. What will happen to the volume of the balloon at that height? Yeah. Specifically numerically, though, what will happen to it? Double. Very good. If you cut the pressure in half, the volume should double so that the two sides remain equal. 1 times 1 is 1. Then we got 0.5 times V, therefore 1 over 0.5 equals V2, and 1 over 0.5 is 2. So cut the pressure in half, the volume doubles. Double the pressure, volume gets cut in half. Basically, they are directly inversely proportionate to each other. Now, for a more extreme example, this is also what is used to pressurize gas tanks that are under a high amount of pressure and have a lot of gas stored inside of them. I've listed here as an example a helium tank, but this includes any gas stored within a pressurized vessel. So like medical oxygen tanks or even propane tanks that you get for a grill. As long as it is some gaseous material forced into a container under pressure, then you have pressure manipulating the volume of that gas. Any questions before I erase the first one? So, as an example, let's say you go to a party store to get a 1 liter tank of helium. Liters are a unit of volume, like with soda. And a standard party tank that you might get at insert party store of choice here might have a pressurization level of 15 million pascals, which is not outside the realm of possibility. That is an actual pressure listing on actual commercially available gas tanks. So pressure 1 is 15 million. Volume 1 is 1 liter. It takes this much pressure to get the helium in that tank down to this size. My question is, how much space does that gas instead take up if you let all of it out and let it assume normal atmospheric pressure again? Bless you. Inside the tank, the pressure on it is 15 million. If you let all of it out, the pressure on it is normal atmospheric pressure, which is the 101,325 we've been using. At that dramatically decreased pressure, what happens to the volume of all that helium? Once let out of the tank, that is enough helium to fill 148 liters worth of balloon. 148 soda bottles worth at standard pressure, which is a lot. There is physically a lot of gas jammed into those tanks, whatever gas is currently held within them. And that is why you should always exercise caution when moving or using tanks filled with anything. Even helium, which is not combustible nor toxic, it's still under a lot of pressure, and so if the tank starts leaking, all that gas could eject out at once and cause a type of explosion, which would be only made worse if the tank was instead filled with propane, which burns. So, you know, any pressurized tank, be careful. Sound good? All right. So, gases do compress. You can make a hydraulic-esque system that uses them. You just have to work around the fact that they compress. Whoops. There is one last thing I want to talk about, one last main thing, and mostly just kind of want to talk about how the concepts we've already discussed cause flight. Because as it turns out, flight is just a manipulation of air pressure. I want to at least briefly talk about how that is accomplished, if you were ever curious. When I was a kid, I would see birds flying, and I thought, why can't I do that? Literally one of my motivations for taking science classes when I was 6 was to try to figure out how to beat gravity. I didn't figure it out. But at the very least, I now understand how flight works. So, to briefly explain, first principle related to flight, you can manipulate the speed at which gases, well, any fluid, flows. You can manipulate flow rate. All fluids, either liquid or gas, can flow because they don't have definite shape. And you can change the speed at which they do so. You might have done this before if you've ever taken a garden hose and put your finger over the end of it. Because without any sort of a nozzle on it, the water ejects out at a certain speed. But have you or someone around you ever taken their finger and partially covered the end of the nozzle and the water starts coming out faster? It doesn't even have to be with the garden hose. Frankly, your shower head does the same thing. When you adjust which setting the shower head is on, notice that the thing has different size holes on it and the water ejects faster out of the smaller ones. In physics, we call that the continuity equation. Basically, the bigger the opening that the water can flow through, or the fluid can flow through, the slower it goes. And the smaller the opening it can flow through, the faster it goes. So you can manipulate flow speed, basically, which is very useful for loads of different purposes. But to talk about how this affects flight, there's another concept I need to tie into it. Because this by itself doesn't cause flying. your garden hose doesn't take off. Second thing related to this that we need in order to achieve flight on this planet is something called Bernoulli's equation. And what this says is, my formatting is a little off. What Bernoulli's equation says is, the faster a fluid moves, the less pressure it exerts on its surroundings, or the less internal pressure it has, which might sound counterintuitive. You might think if it's moving faster, it probably acts with greater pressure on things, and that is true if you're counting the pressure when that gas hits something straight on. But that's not what's happening here, and that's not what's happening in flight either. In this picture, the gas is not colliding with anything straight on as we manipulate its speed. Instead, what we have here is gas flowing through this glass nozzle here. The gas flows this way, so it doesn't collide with anything. And in reference to the previous concept, please, we can manipulate the speed of that gas by changing the size of this particular glass pipe. Basically, there's this narrow spot in the middle here, and as the pipe narrows, the gas should flow faster through that particular point. Now that's what's happening at the glass nozzle at the top. The liquid part underneath is something a little bit different. These three hoses going down from here, they're connected into the different parts of this nozzle. This first one is connected here, before it narrows, therefore the gas here is moving slower. This one is connected after it narrows, so the gas here is moving faster. And this point is after it widens again, so the gas should slow back down. And these three hoses are connected down into a liquid reservoir. And notice these air pressures are pushing on the liquid with different amounts of force. Basically, this spot here, since the gas is moving slower, it exerts a greater internal pressure and is able to push down on the liquid more strongly than this spot here, where the gas is moving faster. Therefore, it exerts less pressure on the liquid, and therefore it doesn't push the liquid down as strongly. The pressure decreased with velocity. That may still sound weird and counterintuitive, which is allowed. Sometimes my brain still has issues with this one. I'm bringing this up, again, to explain how flying works. Because on planet Earth, within atmosphere, you either need rockets that are so strong that your wings don't matter, or you need wings. And birds and planes have wings, so we're going to talk about how wings generate flight. Wings are always shaped in such a way to force air over the top of the wing to be moving faster than the air underneath the wing. Basically, the wing is shaped such that the air will collide with the front of the wing, and that physically pushes and forces that air up and faster over the top than the air that just goes underneath the bottom. Because here it doesn't have to collide with anything, it moves at the same speed. But at the top part, when air collides with the front, it's forced up and over at a greater speed than underneath. And that speed difference is the key to flying, because the faster air up top exerts less pressure than the slower air on the bottom. So you've got less pressure acting inward and down on the top than you have underneath. The slower air underneath exerts more pressure in and up than the slower air up top does. And this, kind of like buoyancy, creates a net force upwards on the surface area of the wing. Flying is just using airspeed to manipulate air pressure, generate enough of a pressure difference to create lift like the balloon. So they are kind of floating in air when planes and birds fly. But the air has to be moving in order to get this to work. That's why planes have to get up to very fast speeds to be able to take off. The plane has to speed up to the point where the wing is actually creating enough of a speed difference to generate that needed amount of lift. And that's why if they're just sitting still, they can't take off. Same with birds, technically. They have to flap in order to get themselves upwards if they are starting from rest. So, that is why wings were invented. Questions? All right. That is it for the chapters about pressure, which are 13 and 14. Please have an excellent break. When we resume, bless you, we'll start looking at something new. I'm planning waves once we resume. Let me know if you need anything or have any questions. Please have a wonderful day and break.